today's experiment, we'll start with two letter A's. I want you to notice how they are both perfectly identical in every way. We're going to place these two identical letter A's onto two different parts of a bike wheel. There we go. Then we'll spin the wheel and we'll see which one is harder to read and why. Now you understand what we're looking for. So we have two letter A's that are the exact same size, with one of the A's located at a point near the axis of rotation. We'll call this A1. And the other is located at a point near the rim, which is much further away from the axis of rotation. We'll call this A2. What you should notice is that as the wheel spins, the A that is nearest the axis of rotation is still easily recognizable as the letter A, but the one near the rim is too blurry to read. In this video, we're going to talk about why objects placed on the edge of a rotating body seem to move so much faster than those placed closer to the axis of rotation, even though they're rigidly attached. Now, there are two ways we can describe the motion of a rotating object, but first we need to establish a coordinate system. Perfect. Okay, now the first way we can describe the rotating object is to talk about the object's angular velocity, which is how fast the object rotates through a given angle in a given period of time. The other way we can describe the motion of a rotating object is to talk about the object's tangential velocity. We write this as a v with a subscript, indicating that it is a tangential velocity. And that's going to equal the total arc length that a point on the rotating object travels, divided by the time it took to travel that far. But first things first. We're going to start by calculating the object's rotational velocity, also known as the object's angular velocity. We can write the angular velocity, or omega, as equal to the change in the angular position of the object, or delta theta, divided by the time it takes that object to rotate through this angle, or delta t. Now let's suppose this wheel rotates through an angle of 90 degrees. In radians, this would be equivalent to pi over 2. If it takes this object 0.25 seconds to rotate through those pi over 2 radians, then we would be able to solve for the angular velocity of the object by dividing pi over 2 radians by 0.25 seconds for an answer of about 6.28 radians per second. Note that because it's a rigid body, all parts of that body will be moving together, and the whole thing will be turning at the same rate. This means that 6.28 radians per second is the same angular velocity for every single point on that tire. This is because every point on a rigid body will always rotate at the same exact rate. Now, if we want to calculate the different tangential velocities, we would need to start with the arc length formula to figure out how far these 2 points have traveled. Let's stick with our example from before and say that A1 is 5 centimeters away from the center of a tire, and A2 is 55 centimeters away, and they both rotate through an angle of pi over 2 radian. As you can see, the radius of A2 is 11 times longer than A1, and this results in an arc length that is also 11 times greater than the arc length of A1. So now we've solved for the angular velocity, and we've solved for the arc length, and we're ready to put this thing into terms of tangential velocity. Remember, a point that is farther away from the center has to travel a greater arc length to keep up with the object closer to the center, and because they're rigidly attached, it has to do so in the same amount of time. This means that objects further from the center will always travel faster than those in the middle. To find out how much faster, we use the equation v tan equals radius times omega. And since we know omega can be rewritten as delta theta over delta t, we can rearrange the terms of the equation to solve either in terms of arc length or in terms of angular velocity. In our case, it looks like A1 is traveling at a speed of about 0.3 meters per second. And it looks like A2 is traveling much faster at a speed of almost 3.5 meters per second. So even though both points are rotating at exactly the same rate with exactly the same angular velocity, the object at the edge will always have a higher tangential velocity than the object closer to the center at a ratio proportional to their radii. So make sure you always pay attention to your rigid bodies and don't confuse your tangential and angular velocities, or else your A's could turn into